Okay. What we have seen in the previous class in a nutshell was this: we are considering a filtering, optimal filtering problem like this. There was a random process x n, it was passed through a FIR filter W 0 dot 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 W p. Instead of p, as I told you, I will be changing it to some other thing now, because I am using p as a vector for some other context. So, W 0 to say W L. So, L plus 1 coefficients, output is y n, there is a desired response d n, the error is. So, you try to minimize the mod square of this error, okay, with respect to the filter taps, because this E of, in fact you can call it epsilon square, is independent of n because of stationarity. This quantity you have seen is a quadratic function of W 0 dot 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 up to W L. We have also found out two things. One is, if we calculate the optimal filter directly, W cap is R inverse P, where R is E x n transpose, P is E x n d n. Okay. Other thing you have seen, the gradient. This in the morning you have seen for a particular W, it was twice R W minus P vector. This you have seen. Now, one thing is that you can find out the optimal filter directly by R inverse P, but suppose you do not have to follow this path. Suppose you do not know how to compute the inverse of a matrix. We can propose an alternative method, which is iterative method, so that as the iteration progresses, finally the filter weight W converges on what is called the optimal weight. We now propose an equivalent technique, okay, that is called method of, that is an iterative technique, it is called method of steepest descent. Now, to explain that, what we do first, we just take a very simple case of single coefficient, say epsilon square, say W, only one coefficient. You can easily generalize this treatment to multi coefficient case, okay, there is nothing, not much loss in terms of generality. Okay. Now, we know epsilon square is a quadratic function of the filter taps. Here we have got only one tap, that is W. So, epsilon square will be a quadratic function. Any quadratic function has got only one minima or maxima, in our case minima, because we are looking, we know that there will be a minimum mean square error only. And then if from that minima, if you move towards your right or left, as you move further away, the epsilon square can only grow, it can never decay, because if it grows and then slightly decays, again there will be a local maxima, that is not possible. So, as we go further and further from that minima point, optimal point, minima point, the epsilon square only has to grow, there is a gradient is always positive. I mean, as you are growing outward, okay, it is only growing. Okay. For that matter, it could have been like this. This is your optimal point W cap. Okay. If that be so, we propose an iterative procedure like this, that suppose at ith step of iteration you are here, W I. What I do at from W I, we have to find out a W I plus 1. Okay. What I do, I look at the gradient here. Okay. The gradient here is positive, because I am to the right of W cap. So, gradient here is positive. So, what I do from W I, suppose I subtract a quantity proportional to the gradient. Proportionality constant is a mu by 2, this is a proportionality constant. This 2 I am just introducing, because it will cancel some other 2 that will come up soon. So, this is a proportionality constant mu by 2 times the gradient, that is del epsilon square del W at W equal to W cap, and I call it W I plus 1. Suppose I do that here. What is happening? Here the gradient is positive. So, that means del epsilon square del W sign is positive. So, that means from W I am subtracting something which is positive, because mu is a positive number. That means from W I am not going further to the right, but I am coming back. So, in fact, I am approaching W cap, is not it? On the other hand, if I am here, say, if instead of here I was here, then gradient here is negative. So, negative and negative positive. So, I add some positive quantity to W I here, and again that is perfect, because from W I then go to the right. So, I am again approaching W cap. So, if I am to the right of W cap, I approach it. So, I go backward. If I am to the left of W cap, I go forward, that is again I approach it, because in one case gradient is positive and therefore I subtract, in another case gradient is negative and I add. Further, if the gradient magnitude is high, in the case del epsilon square del W, its magnitude is high. So, I jump from W I jump to the next point W I plus 1 by a bigger margin. Okay. By step by which I jump is bigger, because there is a difference between W I plus 1 and W I, its magnitude is larger. Okay. I jump by a bigger. On the other hand, if the gradient is small in magnitude, I just crawl, because this term which is called the update term or correction term, that will have small in magnitude. So, from W I just go to a very close point W I plus 1. So, that means when I am further away and the gradient is high, I come close to W cap very fast, but when I am close to W cap, then I do not move much, I approach W cap slowly. So, maybe I can go like this, one iteration, then I go like this, then this, then this, then this, and finally I converge. Okay. Here one thing is important, that your mu should be chosen carefully. If mu is chosen, suppose mu is chosen very small, so naturally this term, this is very small in magnitude. So, you just scroll from here, you go here, then here, then here, then here, then here, then here, like this. It takes a lot of time, many steps of iteration to converge to W cap, but at least you are bound to converge. On the other hand, if you take mu to be large, then what is happening? Your rate of convergence is faster, you jump so much, then so much, then so much, like that. But there is a danger. If you take mu quite high, it can so happen that you jump here, this point, and then from here again here. So, you oscillate along this line, you never come down to W cap. So, you never converge. Worse could be if you from here you jump to this point and then to this point and then this, so diverge out. So, that means there should be some upper bound of mu, and mu should be chosen less than that. Those upper bound expressions in this case are worked out, but I will not go into that, because I am not so bothered about the steepest descent algorithm. I want to derive an adaptive filter algorithm from this. So, in the more general case, what does this mean then? When you have got not single tap, but multiple taps, from W I vector you go to the W I plus 1 vector, I is the iteration index, by what? Subtracting from W a quantity proportional to the gradient vector. You evaluate the gradient at, sorry, this was I was making a mistake here, this was W I, sorry. Okay. So, actually what I am doing here is nothing very different. Instead of treating each weight separately, I am putting all the weights in a vector form, and this del W epsilon square is what? It has got all the gradients put in a vector form, that is del epsilon square by del W 0, del epsilon square by del W 1 dot 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 dot. So, from each W I am subtracting the corresponding gradient by multiplying by proportionality constant mu by 2. And now I know, and this method is called steepest descent. Steepest because wherever gradient is positive, I am just following that path going in the opposite direction. Okay, I am following, I mean by which path I am following? If the gradient is positive, I am following because I am approaching W cap. Even if gradient is negative, I am following because I am approaching W cap. By which path? I am following the path of gradient. That is why it is called steepest descent. I am not going in other directions. Okay, I am following the steepest descent. It is called steepest descent. Descent, steepest descent. Okay. Now, we know what is this expression del W epsilon square. In the previous slide only you have written it. So, you can put that back here. What you get? Sorry. B by 2 and there was a 2 R W minus P, right. So, you can put a P plus here, P minus R W and W equal to W I for this thing, and 2 cancels. This is the steepest descent algorithm. Mu, there is an upper bound for mu for convergence. Those theory I am not going into, because I am not so much bothered about this steepest descent as such, but from this I will derive an adaptive algorithm. Now, suppose you do not know what is R, input is coming, you do not know its autocorrelation function, you do not know the P vector, and further this R and P, they are not static. From time to time they change, because the scenario, okay, the context changes, the scenario changes. Okay, so, input statistics or the all this, input statistics changes, the joint statistics between desired response and input, that is P vector, that changes. So, obviously, there is no fixed winner filter. For one set of R and P, you have got one winner filter. After some time, if that R and P changes, you got another winner filter. So, that means, I mean, you have to adapt yourself from by just looking into the data, and you have to generate the corresponding winner filter by some by some adaptive method. Okay. Next time when the input statistics changes or P vector changes, you again adapt yourself and approach the then corresponding winner filter, so on and so forth. If you want to do such a thing, I propose this. Then suppose I want to carry out this iteration in time, that is iteration index n be I be given by n. So, at 0th clock cycle I carry out the 0th step, at first clock cycle I carry out the first iteration, second clock cycle I carry out the second. So, just for some fun I am doing the iteration in time, same iteration. So, instead of iteration index I can change it to n, number 1. Number 2, we know P vector. What is P vector? E of x n d n, right. X n we know, it is a vector that has x n minus 1 dot 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 up to x n minus L, that times d n and expected value. Now, suppose I want to have an estimate of this, what will you do? I will be using the sample averaging technique, that is I should have x n vector. I suppose you know what is x n vector, for your sake I am writing again x n, earlier it was P, now it is L, this is x n vector. Okay. So, ideally what you should do, you take one case x n d n, take another vector x n minus 1 d n minus 1 dot 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 dot, take many n minus a capital N d n minus capital N. So, this you add and then divide by n plus 1, this just a sample average technique. That will be some good estimate, if n is large, that will be a good estimate of P, you can use that. But suppose I say that look, I will be using not a very good estimate, just a very weird, wild, bad estimate, I do not mind. That is, instead of so many terms, I have only, that is P I approximate as, sorry, simply x n d n. I agree the estimate will be not a good one, and therefore, there will be many errors, but we will see that errors will not affect the convergence much, that we will see. Similarly, x n vector, sorry, or so, we should have x n into x n transpose plus x n minus 1 into x n minus 1 transpose plus dot 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 many terms, and then add and divide by the number of terms to have a good estimate of power. But again, like above, I will be following a very weird path. very, I mean, I will not, I will take a very rough estimate, just x n x transpose n. If I put them here, what do I get? If I make the substitution, w n plus 1, I has become n plus mu, E is x n d n, and then x n x transpose n w n. Okay, take x n out. That means w n plus 1 is w n plus mu x bar n, take common, d n minus x transpose n w n, and x transpose n w n is same as w transpose n x n, because A transpose B and B transpose W are same. You can also write this as w transpose n x n. And what is w transpose n x n? At any index n, w transpose n gives the filter coefficients w 0, w 1 up to w l. They multiply the elements of x n vector. So, what you get here is the corresponding filter output at index n, and d n minus y n is error E n. So, that gives you this algorithm. Okay, this is the celebrated LMS algorithm. There are many theories associated with this. I will not, I do not have time for it. I will just write down the equations. That is, maybe the starting value is all 0. Then for n equal to say 0 to final, that is, final is the time index up to which you will run this iteration. What happens? You find out first filter output y n as w transpose n x n, then E n as desired response minus y n, and then you go for the next set of weight coefficients, filter coefficients. Okay. And so, this is a real time algorithm. You see, the moment we replace I by n and used some estimates, real life estimates, real time estimates for R and P matrix, R matrix and P vector, everything is data dependent. Okay. There is no E operator here, there is a direct data vector x n multiplied by W transpose giving y n, then E n, and x n vector is used along with n to update the weight for next index, so on and so forth. This is an adaptive algorithm. What it does? So, we do not need any longer any information about R and P. This algorithm, we have brought in some approximation because R and P were not replaced by their good estimates, but for bad estimates. For that, that is why we pay some price. This algorithm does not converge in the absolute sense. It is not that W n vector will converge to W cap as limit tends to infinity. No, this is called absolute convergence, that each step approaches is the corresponding optimal value. This does not happen because I told you we have not replaced R and P by the exact values, but by some very weird estimates. But what does converge is the mean of these. So, the filter weights keep dancing, keep changing, keep fluctuating, but as time progresses, the DC for each filter tap, the DC value across which it is fluctuating, that DC value converges to the corresponding optimal value. So, it could be like this, one particular weight say W k n, it can be like this. Finally, it can go like this. This could be the DC value. Obviously, you should also see that this range of variation around the DC value, there is optimal value is not much, Okay. Actually, this is related to what is called misadjustment. This if this spread, if this range of fluctuation is more, we say there is more misadjustment and vice versa. This before I go to that misadjustment, let me tell you one thing. This convergence will take place not always. It will take place provided you take mu within a range 0 and less than 2 by what is called trace of input correlation matrix. What is trace of a square matrix? It is the sum of diagonal matrix, diagonal elements. Sum of all the diagonal elements, there is a trace 2 by that. If you do that, then it is guaranteed that the mean of the filter weights will converge to this. Now, this misadjustment, or we sometimes call excess mean square error, because even with the DC weight, there is some value for epsilon. Even with the optimal weights, this quantity, this has got some value. It's minimum, I agree, but some value. But if you don't put the optimal filter, naturally the error is not minimized. So, that time, okay, that time this epsilon square is more, something more, not this epsilon mean square, but there is something, some extra term delta. What is epsilon mean square? That is, if you really put the optimal filter weights, find out the En and find out its variance, that is the minimum possible error variance attainable, that we call epsilon mean square. But when the filter weights are not the optimal ones, and as we have in the LMS algorithm, filter weight is not converging on the optimal value directly, only its DC value, average value, expected value converges. So, that means here the error variance will not be the epsilon mean square, because we are not using optimal values of optimal this Wiener filter for all indices as n tends to infinity. It is only fluctuating around the optimal filter. So, therefore, total epsilon square will be not just epsilon mean square, but some extra positive quantity delta will be there. This is called excess mean square error. This excess mean square error can be minimized if you take mu less and less. For less mu, this will be less, but the price you pay is this. If mu is on the higher side in this range, the rate of convergence is faster, it converges faster, but the fluctuation will be more around the optimal value. If on the other hand mu is on the smaller side, rate of convergence will go down, it will take more time to converge, but this misadjustment or this excess mean square error delta, that will be less. Okay. Now, when you use an adaptive filter, what you do then? You see, we need En. That means there is actually a training phase in an adaptive filter, during which the desired response Dn actually is given to you, given to the filter, and the input Xn is given. So, you find out output Yn, then found out En, and use the En in that LMS algorithm to get the next filter weight Wn plus 1, so on and so forth in the iterative algorithm. So, during this phase Dn is actually available, and you train your filter, so that from Wn to Wn plus 1 to Wn plus 2 to Wn dot you get better and better and better estimate filter value, and so that the at least in mean the filter weights converge to optimal value. Once the training phase is over, you have no other option but to trust the filter coefficients as to be the best possible one that you can have, and use them as a good substitute for W cap and do the filtering. So, that output may not be very close to Dn, but will be somewhat good estimate of Dn, you have to be happy with that. If after some time input statistics changes, again you use new Dn. So, that is why this filter is trained from time to time, maybe after every half an hour you dedicate some some particular time period as training period, give a Dn, take input and train the filter. So, adaptive filters are trained periodically. This is a convergence rule and all that. Let us take some example. There are many practical applications of these adaptive filters. Unfortunately, in half an hour's time I cannot cover them. Consider what is called echo cancellation. In whenever you speak to somebody in overseas, sometimes you might have heard that an echo of your voice is coming to your ear, which is very annoying and disturbing. It affects your your hearing the other end speaker. What happens there is that to this end, suppose this signal is going, then there is something called hybrid. what happens, what this hybrid does is this, it takes the input signal, okay, and diverts it to this side, to the speaker, and takes the speaker signal and diverts it to this side. Okay. So, no part of the incoming signal gets leaked to this side, but often what happens, the hybrids are not faulty. So, part of the signal, if the input, this signal is say x n, part of the x n, some function of x n comes out as an echo, and that goes travels to the other side, it reaches the ear of the speaker, original speaker on the left hand side as an echo. To avoid that, what you have to do, we model the hybrid as a linear time invariant system, usually of very high order. That is, here you forget this for the time being, as though this is a filter H n, n from 0 dot 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 say L minus 1, very large order filter, and the thing that comes out here is echo. Okay. What comes out here is echo plus this person's speech. If this person is speaking, so what comes out here, x n convolved with this sequence, that is the echo plus this person's speech. So, maybe instead of doing it here, this is the model actually. The echo is generated, say E n, and this is this person's speech, say S n. So, S n plus E n, if you call it D n, it is D n which goes to the left hand side. So, not only S n, but also E n, that is the echo comes back to the original speaker. To avoid this E n, if I can, if I put a filter here, adaptive filter, dot 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 same order, say W L minus 1 n, use this signal as its desired response, take the error, this is error. So, this is not E n, let me change the symbol E n to something else, let me call it echo, echo n, and this is E n. And if I use the E n, this is a symbol to update, to adjust this filter weights by the LMS algorithm, so they are adjusted by the LMS algorithm by this E n. What will happen? Then these filters, if everything else is done properly, this filter weights will finally converge to, at least in the sense of mean, it will converge to this H n. If it is actual, if the misadjustment is very small, what will happen? They will actually converge to H n, but for very small difference. In that case, the two outputs will be same. If it generates echo n, it also will generate echo n, because input is same for both. So, if you take echo n and subtract from D n, you once again get back E n equal to S n. So, which S n, the S n goes that has no echo or very little echo, this is called echo cancellation. Okay. This echo cancellation is particularly useful for data modems, because human beings can still, using their intelligence, can differentiate between echo and actual sound to be heard, but data, if it is data modem, a computer cannot. Okay. So, echo cancellation for data modem is very essential. Take one more example, equalization in communication. In digital communication, what do? You are transmitting sequence of symbols. There is an alphabet A of various symbols, alpha 0, alpha 1, dot 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 dot, finite alphabet. So, there is a sequence, what you transmit is a sequence of symbols, you know. Symbols can be complex like A plus JB, you know those I component, Q component, all that. So, that IN is the symbol sequence, IN element of A, that is I0 is one symbol from here, I1 is another symbol from here, this is a symbol set you transmit. But essential problem, one of the main problem in communication is that even if your symbol sequence to be transmitted is discrete, the media through which they will travel, that media is continuous or analog. So, for transmission of such discrete messages, you need an analog pulse to carry that information. Suppose that pulse is designed like this, that okay, there is a basic pulse, so value could be 1 pt, you trigger it here, observe it here. Now, suppose with this pulse, you have a thing like this, you multiply the pulse by I naught. So, height will be I naught. You trigger it here and measure it at the receiver at this point of time, say capital T. But since you are transmitting fast, you will not wait for time up to capital T, you might trigger the next pulse at tau and multiply the pulse by I1 at minus tau, you triggered another pulse. So, I minus 1, so on and so forth. So, at the receiver, if you want to measure at capital T, if you sample, you will see there is from this figure it appears there is an interference from this pulse, from the right hand pulse and the left hand pulse, in fact from many right hand pulses, from many left hand pulses, that gives us to intersymbol interference. To avoid that, we design the pulses so that at capital T, when I measure this guy, all other guys should go through this zero crossing. That means, in general, you design the pulse so that at n t, at tau equal to 0 is started, measure at capital T, then at tau you switch on the next pulse, so on and so forth, and measure it at t plus tau. Okay. At n tau, you suppose triggered one pulse, and this is n tau plus t, this is okay. Then the pulse to the right of this should pass through 0 here, pulse to the right of that also should pass through 0 here. So, all other pulses to the right of this and left of this should cross through 0. That means, P the center point minus k tau should be equal to 0. K can be both positive and negative. This is called zero forcing condition, like a Nyquist pulse, you know, this sync pulse for that matter. The pulse we have shown, it does not follow this zero forcing condition, but look at this pulse. Suppose this is your center point and this much is tau, this much is tau, like that, this much is tau. So, as you go to the left by tau or 2 tau or 3 tau or to the right also by tau, you have 0 crossing. So, this will ensure that there is no intersymbol interference. Okay, so, we design such pulses, these pulses are called Nyquist pulses. Problem is, so that means what you transmit is I n p t minus n tau. Okay. Problem is this pulses pass through the channel and the channel is not ideal, it is not an ideal system. So, P t convolved with channel will give rise to some P prime t, and this P prime t will no longer satisfy the zero forcing condition. So, obviously, I will get back this what I will receive is say G t as I n P prime t minus n tau. So, that means I will have intersymbol interference. If I want to find out, say, if I want to sample this at a particular tau, say the summation is over n. Suppose I want to find out at k tau, k t, I sample. What will I get? I k p prime k t minus n tau plus say I k plus 1 p prime sorry, this should be k tau plus t. It was triggered at k tau and I am sampling at t further to the right. So, k tau plus t. So, k tau plus t and then k plus 1 tau plus t minus n tau, so on and so forth. These terms pulse will not be 0 because zero forcing has been demolished. As a result, you will get a combination kind of stuff, that is I k times some constant plus I k plus 1 times some constant, I k minus 1 times some constant, so on and so forth. Those constants are coming from p p prime t, and p prime t is what? Convolution between transmitted pulse and the channel impulse response. Okay, that means you get a discrete time model, that if you sample it, what you get? Receive sequence say R n is nothing but convolution, that is I r, sorry, not r, I have used I m sub h n minus n. Okay. That means, that is the equivalent model is this, that you are transmitting a sequence I n, there is a channel whose response is h n and you are getting this R n. Maybe since I am putting everything in subscript, let me put this also in subscript. So, R n is no longer I n. That means, what is R z? That is I z times H z. So, what is I z? That is R z by into 1 by H z. Now, that means, if I take this, pass it through a system 1 by H z, what will I get? I should get back I n. Problem is H z is what? Is just a z transform of the sequence H n. It is an FIR sequence, because you know the intersymbol interferences are only from adjacent neighbors and not from very far away pulses. So, those coefficients, you know, they die out, those coefficients which are related to far away pulses, they die out. So, it is FIR sequence, but FIR sequence its z transform is say H z, and I have no control on the roots, that is on the zeros of this FIR polynomial. So, in general some of the zeros can be within unit circle and some of the zeros can be outside the unit circle. So, 1 by H z is a filter where for zeros of H z becomes pole here. So, some poles are within unit circle and some are outside unit circle. So, it is a stable but non causal system, something like this, 1 by H z. So, if H prime n corresponds to, or maybe H I for inverse here, because this is the inverse system, corresponds to 1 by H z, it will be cause stable, so absolutely summable, but it will be non causal. since it is stable and therefore absolutely summable, it will die out. Any stable system impulse response has to die out after some time, because if they have appreciable value all along, then it is not absolutely summable, it is not stable. So, that means we can truncate it maybe up to capital N and minus n, and beyond that we know it is already 0 and 0 or very close to 0. So, truncate it. Now, this is your HIN, and this is not realizable in practice, but if I have Z inverse n 1 by Hz, the corresponding filter response will be what? Delayed version of this, delayed by capital N, and that will start here. To n minus 1. This is realizable because this is causal. So, if what I will do, I will construct a filter z to the power minus n by Hz, and what will I get here is not I n, but because is z to the power minus n, you can club with R n. So, R n is actually getting delayed by n cycles passed through 1 by Hz. So, what we will get here is not I n, but I small n minus capital N. This is called equalizer, linear equalizer, which equalizes the effect of the channel. Okay. Problem is, if I really know the channel, I know Hz, and therefore, I can construct this. Unfortunately, channel is often not known, and if channel characteristics changes from time to time. So, we have to do some adaptive filtering, and then it becomes an adaptive equalizer. So, what we do there is the following. There is a training phase during which the transmitter transmits some known sequence I n, which is also known to the receiver. A standard sequence is called pilot sequence. So, receiver knows what the equalizer output should be ideally, that is what was transmitted. So, what it does, it takes the received signal R n, it constructs an adaptive filter, because this equalizer is a causal FIR system of length 2 n as I showed. So, you construct an equalizer maybe from W 0 dot W 2 n minus 1. Okay. This output should be as close as possible to what? Not I n, but I n minus n. I n is what? The transmitted sequence, the pilot sequence. You just delay it by capital N, because you know that your channel could have been, this equalizer actually is non-causal, but you have made it causal. So, there is a delay that has gone into the system. So, that means desired response also has to be delayed, and use the corresponding E n and use it to adapt it. What is the equalizer? This is trained properly. This will approach this equalizer z to the power minus n by Hz, and therefore, output will be a good estimate of I n minus capital N. This is called adaptive equalization. There are many other applications of adaptive filter. I will not, you can consider this beautiful book, this wonderful book by Heikin. Okay. Then there is a book on adaptive filter by Woodrow and Stearns. Woodrow was the inventor of LMS algorithm by Bernard Woodrow, and Stearns. Okay. All right. One more example I can consider, and then I can wind up. System identification. Suppose there is a plant, this is modeled by some FIR system W 0, W 1 dot 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 W L minus 1. You are observing it, you do not know the coefficient, there is a sequence, that random sequence x n that goes in, we put an adaptive filter here. Sorry, instead of using W, let me use some other symbol here. H0 H1 dot 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 HL minus 1 and there is a measurement noise Vn, together is Dn. This measurement noise is uncorrelated with Xn and therefore uncorrelated with this output Yn. Okay. Now, what is the optimal filter here? Dn, that filter which corresponds to what? The orthogonal projection of Dn on what? On the space spanned by Xn, Xn minus 1 up to Xn minus L plus 1. Maybe instead of L minus 1, why even L minus 1? Make it L. That is, if you consider this space spanned by these fellows, Dn must be, what is the best filter? What is the optimal filter here? The orthogonal, the one that gives the orthogonal projection of Dn on the space spanned by them. What is Dn? Yn plus Vn. So, that means, what is the projection? Projection is a linear operation. So, projection of Dn on the space spanned by them is same as projection of Yn on the space spanned by these fellows and projection of Vn spanned by these fellows. Now, you see Vn is uncorrelated with them. So, Vn is orthogonal to each of them, because Vn is uncorrelated, and if Vn is orthogonal to each of them, then that means projection of Vn on them on the space spanned by them is 0, is not it? It is like this situation. If it is not orthogonal, you have got one projection of a vector V, you can call it V cap, you can, and is the error E. But if V itself is orthogonal, then V cap is 0. So, Vn, the projection of Vn on the space spanned by them is 0. So, projection of Dn on the space spanned by these fellows is same as the projection of Yn spanned by on these fellows. Okay. Now, what is the projection of Yn? What is Yn after all? Yn is H0 Xn, H1 Xn minus 1. So, Yn is already given as a linear combination of Xn, Xn minus 1 up to Xn minus L. So, Yn already lies in the space spanned by Xn, Xn minus 1 up to Xn minus L. So, projection of Yn on that space is Yn itself. So, that means this output here for the optimal filter case should be Yn, and therefore, W0 should be equal to H0, W0 should be equal to H0, W1 should be equal to H1, WL should be equal to HL. So, since optimal filter is not computed, it is computed in adaptive way. So, you put it in the adaptive filter framework, this is Dn, this is Yn, this is En, use this En in the LMS mode to adapt them. So, finally, after convergence, W0 should approach H0, W1 should approach H1, WL should approach HL, so on and so forth. This is called system identification. There are many other applications, adaptive noise cancellation, interference suppression and all that, adaptive beamforming, which is very used in smart antenna applications, where suppose there are two persons, it is very useful in today's mobile communication. Suppose there are several persons, they are using the same frequency band, but sending signal from different directions, and I want to receive only one and I do not want to hear others. So, I will be adjusting my antenna weights, so that a beam is formed, that is antenna gain is maximized in only one direction, the direction in which I want to hear, and nulls are created in other directions from which other signals are coming. So, thereby you do some kind of special filtering. Now, here the persons who are receiving the transmission signals, they are in motion. So, their direction changes. So, this business of giving null in certain directions and applying beam in certain directions, this needs to be again adaptively adjusted. Okay. So, that gives rise to adaptive beamformer. So, there are many applications which we will find in this book. So, I will not discuss them any further. I hope you enjoyed this course. Now, probability and random process, there are too many things in this. So, Obviously, in a UG course like this, all cannot be covered. But I feel that whatever has been covered will serve as a good background, and you can now go into more advanced topics. Okay. For instance, you can go into topics like martingales, you can go into topics like queuing theory and things like that. These are all given in, at an introductory level in Papolis's book, and the background that is required for the, reading those, for studying those, that has already been covered. Okay. So, I hope you enjoyed this course, and for any feedback you can contact me, you can write to me or you can contact me. Okay. It will be nice to have a communication with your end. So, you can contact me here. My email address is mritun@ece.iitkgp.ernet.in. Okay. My phone numbers 03222283512, that is office, 283513, that is residence. Okay, then hope you enjoyed this course, and in case you learn something from this, that will be a good reward for me. So, thank you very much for all your attention. Good luck and goodbye.
(1951). A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the N.R. Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape. And IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. At every stage of its evolution, IIT Kharagpur remained ahead of its times. It provided the best of facilities for the budding technologists, helping them shape their own as well as the nation's future. Indeed, today, IIT Kharagpur has blossomed into a time-tested, venerable institute of learning. With the rich experience of converting individuals into brilliant professionals through 50 glorious years. As you cross the campus gate, you feel the distinct nip that is IIT Kharagpur. The spirit of objective inquiry and lateral thinking hangs heavy in the air. The modern township-like campus of IIT Kharagpur, set in sylvan surroundings, is self-sufficient in all respects. From modern banks to the good old post office, from vast playgrounds and well-equipped gyms to modern auditoria and open-air theaters, and from the quiet fiber-optic linked residential quarters for the faculty to the web-enabled hostel rooms for the students. At IIT Kharagpur, lush green bowers of tranquility coexist with smart cards and ATMs. Spread over 690 hectares of sprawling cyber habitat, 120 kilometers from Kolkata, IIT Kharagpur is one of the largest network campuses in Asia. Just the academic complexes itself spreads over a built-up area of about 2 million square feet, of which 150,000 square feet is the new complex that commemorates the Golden Jubilee celebrations. And that's not all. It is the only IIT to have conquered territory beyond its own through cutting-edge courses offered in its extension campuses at Kolkata and Bhubaneswar. Indeed, in this Golden Jubilee year, as the celebration continues,